Hey everybody, Bill Sky, the assembly guy here. Another video. This time we're going to talk about the binary number system. Now in the previous videos we've been doing some cool things with technology and installing stuff and a little bit of programming. But you know something? Assembly language, you have to know something about the internals of the CPU. You have to know something about how the data is stored in the CPU as well as in memory. So what we're going to do today is we're going to go over the binary number system. And then what we're going to do is we're going to do a little bit of programming to show you just how binary numbers and data is stored inside the computer memory. So you're going to get a little touch of debugging. It's actually going to be a lot of fun. So let's get started. So what is the binary number system? The binary number system, it is very simple. It's how computers store numbers in memory. It's also how computers store numbers on storage devices like thumb drives, hard drives, SSDs, even tape drives. It's all binary. It's all ones and zeros. And computers are just a collection of billions of on and off switches. Literally, like the switch on your wall for your light. Just on and off switches. Now they're implemented using transistors and resistors and diodes and things like that, but that's all they are. So on is considered a 1 in the binary number system. Off is considered a 0. So again, on is 1, off is 0. It's also going to be thought of this way. True is 1, false is 0. So that's another way of thinking about it. Now, just like in the decimal number system, which you and I are all used to using, hopefully you're all used to using it, the total number of digits that the decimal number system has is 0 through 9. The binary number system, which is what we call base 2, decimal is called base 10, binary is called base 2, it only has 2 digits, 0 and 1. All number systems begin with 0. That's a very important thing to think about. All number systems begin with 0. So remember, a binary number, as you can see here, is just ones and zeros. In this case, 1011, 110, 1101, 00011. And for those of you that this is the first time you've seen this, it might look a little alien to you. And it kind of should, because we don't, as human beings, think in terms of binary. However, a computer, because it's been implemented with on and off switches, you come up with a better way, I'd love to invest in it. But right now, that's what we've got. Everything is binary ones and zeros. So we have to use the binary number system. One of the reasons why we use the decimal number system as human beings is because we have 10 fingers on our hands. We can count. And then when we reach 10, we have to put a mark in the sand or something like that. Binary, think of the computer as only having 2 fingers. It has to be able to count as much as possible or just as effectively of decimal. So again, computers only have ones and zeros. Each position of a binary number has a decimal equivalent based on the power of 2. So the power of 2 always begins at 0. And we've got a bunch of examples in this presentation or in this discussion. So you can see, starting on the far right, you can see that position 1 has a value of 0. That's a power of 2. So 2 to the 0 is equal to 1. Position 2 is the position 1. Again, everything starts at 0 in computers and computer science. So position 2 actually has a power of 2 value of 1. So 2 to the 1 is 2. Position 3 has a power of 2 value of 2. So 2 to the 2 is 4. And position 4, which has a value of 3, 2 to the 3 is 8. And we're only looking at what we call a nibble here. A nibble is 4 bits. A byte is 8 bits. A nibble is 4 bits. So that's all we're looking at here. However, we can get much bigger. So what does it mean? If the binary number has a 1 in a certain position, you multiply that 1 by its power of 2 value. If the digit at that position is 0, you just ignore it. I mean, you could multiply it by the power of 2, but 0 times any power of 2 is always going to be 0. So I just like to ignore them. So here's an example. So the binary number here is on the bottom. It's 1101. So what does that mean? That means that the 1 under 2 to the 0, we're going to use that in our number. The 2 under the 2 to the 1, we're not going to use that because that binary digit is a 0. The 4 under the 2 to the 2, that's a 1 there, so we're going to use that 4. The 8 under the 2 to the 3, we're going to use that because that's a 1. So then what we'll do is we'll add 8, 4, and 1 together, and I believe that gives us 13. So 1101 is actually 2 to the 3rd plus 2 to the 2nd plus 2 to the 0, we ignore the bit at 2 to the 1 because that bit is 0, so we don't mess with it. And then we add those decimal values up together and we get 13. Now you might say, why in the world did they do it that way? Well, they didn't do it that way. We have to do it so we as human beings can understand what a binary number means to us in decimal, because that's how our brains are wired because of experience and how we were brought up. Everything is decimal. So the computer doesn't do this. The computer does not have to worry about converting to decimal. It's just us doing it. And that's why we're having this discussion today. So here's another one. Let's try another one. So 2 to the 0, there's a 1 at the very bottom, so that 1 is valid. So we're going to use the 2 to the 0 decimal value of 1. We're going to use the 2, which is the 2 to the 1 value, decimal value, because that's a 1. We're going to use the 4 because that's a 1, 2 to the 2. There's a 1 at the bottom, but we're not going to use the 4th bit, the furthest left one, because that's a 0. So we're going to add 4, 2, and 1 together. So 2 to the 2 plus 2 to the 1 plus 2 to the 0. We're going to ignore the 2 to the 3 because that was a 0. If you remember, that's a 0 on the far left. That binary digit is a 0 on the far left, or bit is a 0 on the far left. So we add those together and we get 7. And that's how it works. That's how you convert a binary number to decimal. Now, the larger the word size, which is the size that you're dealing with, that your computer can handle, the more bits that you can have in a binary number. And that's why a 64-bit computer is much more powerful than a 32-bit computer, which was more powerful than a 16-bit computer, which was more powerful than an 8-bit computer. Because the more bits you have, the larger the binary number, which means you can address more disk space, you can address more memory, you can do bigger calculations, you can even do smaller calculations, and that's just how it works. So here's an example of a full byte. And if you notice, let's take a look from the right to the left on the very first row, 2 to the 0, 2 to the 1, 2 to the 2. Notice how it just goes up by a 1 on each power. And the second row, you're just multiplying the number on the right to get the number on the left. So you start at 1, you multiply that by 2, you get a 2, you multiply that by 4, you get a 4, an 8, a 16, 32, 64, and 128. So if you look at the bottom row, we're going to only use the decimal values above that bottom row bit if it's a 1. So we're going to take 128 plus 64, we're going to ignore 32, 16, and 8. We're going to then add 4, 2, and 1 together, and that's going to give us our 199. And that's how the computer understands numbers, is using binary bits, binary digits, and the only reason, again, that we're converting these to decimal is because we are human beings. Now, how do you go from decimal to binary? So we just went from binary to decimal. How do you go from decimal to binary? You know, you've got a number in your head and you're wondering, I wonder how that is stored in memory. Well, the way that you do that is actually very easy. You just take the number, divide it by 2, take the result of that number, divide it by 2, take the result of that division, divide that by 2, until the final result of 0. And what you do is you take the remainder of each one of those divisions and you write that down, and then you flip them, and then that's your binary number. So we've got some examples here. So let's take a look. The number 12. How do we find out what the binary equivalent of decimal 12 is? Well, what we do is we take 12 divided by 2. That gives us a 6 and a remainder of 0. So we hold on to that 0. Then we take 6, we divide that by 2, we get a 3, that as well as a remainder of 0, we hold on to that 0. Then we take 3, we divide that by 2, that gives us a 1, but we have a 1 remainder. You're never going to have any more than 1 when you divide by 2. You may have 0 or 1. So we hold on to that. So far we've got 0, 0, 1. Then we take that 1, we divide that by 2, we get a 0 with a 1 remainder. And then what we do, we take those 4 remainders, 0, 0, 1, 1, we flip them, and we get 1, 1, 0, 0, and that's equal to 12. And you can verify that yourself. The most significant bit of this nibble, 1, is an 8. The 1 to the right of that is a 4. 8 plus 4 is 12. We don't count the 2 zeros because they have a value of 0. Let's try another one. 163. We take 163, we divide that by 2, we get 81 with a remainder of 1. 81 divided by 2 is 40 with a remainder of 1. 40 divided by 2 is 20 with a remainder of 0. 20 divided by 2 is 10 with a remainder of 0. 10 divided by 2 is 5 with a remainder of 0. 5 divided by 2 is a 2 with a remainder of 1. We hold on to every one of those remainders. 2 divided by 2 is 1 with a remainder of 0, and 1 divided by 2 is 0 with a remainder of 1. We take all of those remainders, which was 1, 1, 0, 0, 0, 1, 0, 1. We flip them, and we get 1, 0, 1, 0, 0, 0, 1, 1, and that's equal to 163. Again, the computer doesn't do this. We have to do it as human beings, okay? So, the next thing, simple binary arithmetic. How do you add or subtract two binary numbers? Well, it is very simple. It's just like base 10, except you don't have 9 digits. You only have 2 digits. So in this example, we take 0, 0, 0, 0, we add 1 to it, we get 0, 0, 0, 1. What if we have 0, 0, 0, 1 and we want to add 1 to it? Well, we take the first bit of 1, we add 1 to it. We don't have a 2 in binary arithmetic or binary number system, so that's a 0 with a carry. So we move that carry to the next digit or the next bit in the binary number, and that gives us 0, 0, 1, 0. Let's say we want to add another 1 to that, 0, 0, 1, 0 plus 1. Since that least significant bit of 0 is equal to 0, we add 1 to that, we get 0, 0, 1, 1. The next one, 0, 0, 1, 1, if we want to add 1 to that, how do we do it? Well, we try to add the 1 to the least significant bit of 1. That's a 0 with a carry. The second bit now has a 1, but it also has a carry it has to add to it, which is 0. And then the final result, we take that carry to the third bit. The final result is 0, 1, 0, 0. Let's go ahead and try adding 0, 1, 1, 1. Let's add a 1 to that number. So I'm going to do it along with you here. So I'm going to take 0, 1, 1, 1. We're going to add a 1. And what is that equal to? Well, the 1 plus 1, we know that's equal to a 0, and that carries the 1. That 1 plus 1 is equal to 0. That carries a 1. That 1 plus 1 is equal to 0. That carries a 1. That 1 plus 0 is 1. So that is the answer of 0, 1, 1, 1 plus 1. All right, let's do the next one. We're going to take 0, 1, 0, 1, and we're going to add 1 to it. We take 1 plus 1, that's a 0 with a carry. 1 plus 0 is a 1. There's no carry because we don't have 1 plus 1. So we're just going to drop down the other digits, and that's the answer to that one. 0, 1, 1, 0. And you should try out a number of those things. Or ideas, just come up with bits and add 1 to them and see what you get. Subtracting binary numbers borrows from the more significant bit. So for instance, 0, 1, 0, 0 minus 1. Well, you can't borrow from 0, which is the least significant bit. You can't borrow from the 0 to the left of the first 0. So you have to borrow from the third bit, which is a 1. And that borrow moves to every bit. It copies to every bit to the right. So we get 0, 0, 1, 1. So 0, 1, 0, 0 minus 1. Since the first two bits are 0, we're looking for the first 1 from right to left. So the 1 from the third bit is carried to the right and copied to the right to all the other bits because we took away that borrowed 1. And that ends up being 0, 0, 1, 1. So let's do another one. Let's try another one here. So we're going to say, let's take 0, 1, 1, 1, and let's subtract 1. Well, it just so happens that this is our first 1, so we don't have to borrow at all, do we? So what we're going to do is we're just going to say 1 subtracted from 1 is a 0, 1, 1, 0. And that's our answer, 0, 1, 1, 0. That was a simple one, okay? Let's do another one. Let's take 1, 0, 0, 0, minus 1. And we can't subtract 1 from 0. So we've got to go to the next one. We can't subtract it from that. We can't subtract it from that. But aha, we found our 1 there. So what we're going to do is we're going to take that 1 and we're going to move it to the left. And we copied in all the bits that are less than that, and that's the number we get. Now, if you wonder, what is the decimal value of that? That's equal to 8 because of 2 to the 4. What does this equal? This is equal to 7 because that's 2 to the 2 plus 2 to the 1 plus 2 to the 0, and that's equal to 7. 4 plus 2 plus 1 is equal to 7. So there we go. It's really not that difficult. It might take you a little bit of practice, and the way to practice is just come up with a bunch of zeros and ones and then try it out. Now, one piece of advice, I don't recommend that you just get a calculator to do this, because if you go on a job interview and they ask you to do something like this, and I'm telling you it may happen, they're not going to let you use a calculator. So they want to see that you've educated yourself or you've been educated in such a way where you understand binary arithmetic. Now let's do some debugging. Let's actually get into some coding here. And you're going to see a bunch of stuff here. So what we're going to do is we're going to demonstrate how to create a double word memory area and how the debugger will show its contents in binary. We're going to do that first on Windows, then we're going to do it on Linux. So meet me in just a moment. All right, welcome back. And what we're going to do is we're going to do a demonstration of what binary numbers look like, or what integers look like actually stored in memory. Now, if you haven't done this already, if you haven't started up your Visual Studio, go ahead and pause this video, get it started up, or boot your computer. I'm sure your computer's already booted, unless you're watching this on your phone. But it's a good idea to follow along with me on this, because it'll really give you the experience to be able to demonstrate this to maybe a job interview. So it's always a good idea to do that. So let's get going with this demonstration. I'm going to go ahead and start my Visual Studio. And I'm going to create a new project. Now, I've got a whole bunch of new templates here. If you're interested on how to get these templates so you don't have to do it yourself, or you are having trouble setting up the templates, there's another video on YouTube. I believe it's called Downloading the Komanetsky Templates for Windows. Another one, Downloading the Komanetsky Templates for Linux. Pause this video, go ahead and take a look at that one, and it'll show you exactly how to do that, and you'll get these templates automatically. These templates keep you from having to start from scratch on every single project. So what I'm going to do is I'm going to simply select my Komanetsky. Actually, I'm going to do the Komanetsky ones. Those ones called Irvine, those came from the Irvine Assembler Language book. You can use those too. The code is a little bit different. I'm just going to use this Komanetsky 64 functions template. Actually, no, I'm not going to do that. I'm going to use the ASM template x86. And I'm just going to call this x86 binary demo. Now we're going to do another one with 64-bit, so we do that for Windows and for Linux. All right, and there is my, if that would expand for me. There we go. There's my main.asm file. And the first thing I'm going to do, because this is x86, I'm going to drop down to the right of debug. I'm going to drop down the x86. Now I'm going to go up here and say build and just rebuild solution. If I get an error, yep, it said it failed. Now it doesn't really say why, and I think we might have seen this in other videos. I'm going to clean the solution, and then I'm going to rebuild it, and it should give me a better error. It says, you know, it cannot be found, those tools. So we're going to retarget the solution. So I'm going to right click on solution. I'm going to click retarget. Where is that puppy? There it is, retarget solution. Now, why does this happen? Because those templates were created with an older version of the developer's toolkit on Windows. And this way we are going to upgrade it to the one that we've got because we downloaded and installed the most recent Visual Studio. So let's go ahead and build that. Make sure it builds with no errors, which it did. 0 failed. Awesome. So this is something new. You may not have seen this before, but we're going to go down here below the data, and I'm going to create a byte. I'm going to create a byte. I'm going to create a single byte variable. So I'm going to say byte variable, define byte, and I'm going to give it a value of, I don't know, let's give it a hexadecimal. Let's give it just a value of 192. Now, because we don't have anything at the end of this number, it's considered decimal. If we wanted to make it hexadecimal, we would say H, an O for octal. And that's all we're going to do. So let's go ahead and save. Don't forget to save all. We're going to go ahead and build the solution. And what I'm going to do is I'm going to move to the left of line 12, and I'm going to click toggle breakpoint. There it is. That little breakpoint says the program will stop running at that line. I'm going to click debug, and I'm going to start debugging. And this may be our first adventure into debugging, but debugging is so important for assembly language programming. So what are we doing? Well, if you notice, there's a little yellow arrow right there on line 12. That means our program is currently on line 12. And what good is that? Well, I would like to see what byte variable looks like. So what I'm going to do is I'm going to go up to debug. I'm going to go down up to Windows, and I'm going to select memory 1. You can select memory 2, 3, or 4. Doesn't matter. I'm going to select memory 1. And up here, I'm going to put in an ampersand and my variable name, byte variable. And we can see our byte variable. It's C000. What in the world does that mean? That's hexadecimal. I'm going to right click on that, and I would like to see that as binary, but as you can see, it doesn't even show it as binary. I don't even have the option on Visual Studio to look at that as a binary. I can look at it as a 2-byte, 4-byte, 8-byte, but it doesn't give me any options. I select unsigned. You can see the 192. But it doesn't give me any option to look at it as binary, which is kind of frustrating. But you can see the value 192. So what we're going to do next is, this is one of the reasons why developers love Linux, is what we're going to do next is we're going to go in Linux and we're going to actually show that variable and what it really looks like in the computer's memory. So hang on. All right, we're back. This time, let's take a look at our Linux. It's going to give us a little bit better idea of what a binary number looks like in memory. So I'm going to do the same thing, except this time on Linux. I'm going to open up my home folder, documents. I put all of my assembly language templates in ASM projects. Remember, there's another video out there on how to download the templates that I have available to you guys. And I'm going to open up the Linux 32-bit template. I'm going to right click on that. I'm going to say extract here. Now I can right click on that and give it a name, say rename. I'm going to say x86 binary demo. I'm going to open that up. I'm going to open up main.asm. That opens by just double clicking it, it opens the default gedit, I believe, editor. I'm going to right click on that and say open with Genie, which is a much better editor, and it even lets me build the application. And I'm going to go in there and put byte variable, define byte 192. I'm going to go up to build and say make. You don't want to say compile, you want to say build make. Now you can only do that if you've got my template. If you don't have my template, you're going to have to issue the build commands yourself. I have a thing in here called a make file that Genie uses to build the application. So it built okay. I'm going to go up here and say build. Actually, it doesn't really have the ability for me to, on Genie, for me to say that, to clean it, because I would like to delete. So there's the executable right there. I'm going to delete it. There's the listing file. I'm going to delete it. I'm going to delete the O file. Now I'm going to rebuild it. And you can see that the assembler executed, the linker executed, no problems. So now what I'm going to do is I'm going to right click on the background of the project, and I'm going to say, I like to use the KDBG debugger, /main, main is the executable, and this brings up a really nice graphical debugger, just like you saw in Visual Studio, but it actually has more features. So under For the line 15, the no-op, I went ahead and clicked a little breakpoint, and I'm going to run it. You can see the little green arrow right there, and I'm going to go down here to memory, and I'm going to type ampersand byte variable. We can see our C0 there. I'm going to right click on this. I want to look at bytes. I'm going to right click on it, and I want to look at it as binary. And there is C0. So C0, which is a decimal 192, is 11000000, I believe. So 11 and 6 zeros. I can also look at this by right-clicking on the debugger. Under memory, I can look at it as a hexadecimal C0. And that's binary. That is what binary looks like. Welcome back from our Linux demo. Challenge. What challenges do we have? What can we do to actually learn this stuff a little bit better? Well, a great challenge that I have given students in the past is two of them. Write a program that takes a binary number, convert it to decimal. You can do this in Python, you can do this in C, you can do this in C++, you can even do it in Java. So ask the user to type a binary number and convert it to decimal. You might also want to do some user input validation to make sure they just type ones and zeros and there's no spaces. So really good project to do. Another project, the opposite way. Write a program that takes a decimal integer, no periods, no decimal points, no fractional component, but it takes a decimal integer and convert it to binary and then display it to the user. These are really, really good assignments. These are really good practice projects, and your first challenge. Again, I wouldn't do this in assembler. I don't think you can do it in assembler just yet if you've just started this course, but do it in C or C++, any language you like that allows user input and output, which is just about all of them. All right, so that's it. That's the binary number system. I hope to see you in my next video.